أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم فبأي آلاء ربكما تكذبان. Thanks to Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. Thanks to Allah subhanahu wa ta'ala who has given us one more day, one more chance to repent to Allah subhanahu wa ta'ala. So how to repent to Allah subhanahu wa ta'ala? By thanking Alhamdulillah. Whatever he has given to us, whatever he has bestowed upon us, we need to Alright, so if we look into the highlights of what we have done in the last lecture, we discussed about the definition of Fourier series, what the Fourier series is. Of course, every technique, every method has got some constraints, some prerequisites are there. Just like if you want to come to UET, you have to have 12 years of education, and then you need to compete other students, only then you can enter into this particular place. So same is the case. So every method, every technique does have certain criterions before we go and implement that. Once you get in, try to mute your microphone first, please. So let me do that. I pull them up. All right, so before we move on and go into the solution of a particular function, a function that has to be periodic with specific period defined over the interval, like from minus pi to pi initially, we see that the solution would be written in the form of infinite geometric series. In that series, we need to know those unknown coefficients, the Fourier coefficients, like A naught, An, and Bn. Once we get those coefficients, plug in over here, and then we will be having finally many terms over there. Everything is a formula for the series, the infinite geometric series. Formulas are there to compute A naught, An, and Bn. So all we need to calculate these unknown coefficients. Once we get these coefficients, we can plug in that expansion. So simplify it as much as you can. So normally 3 to 4 non-zero terms are good enough to set the trend. Normally it is going to be a systematical procedure. You will get to know once you obtain a solution to one particular function. So you will see that it will lay down a certain pattern behind the scene. Change of interval is an option, of course, not necessarily every time. It is going to be from minus pi to pi. If, for example, if it is over the interval from 0 to 2 pi, for example. minus pi by 2 to 3 pi by 2, for example. The length should be 2 pi, but the interval, the starting and the end value could be different. So if we do have, yes, we can utilize the Fourier series method. Examples are there. Yes, we see that the interval is from minus pi to pi. The length is 2 pi. The interval is not different, 0 to 2 pi, but the length is 2 pi. The interval is from minus pi by 2 to 3 pi by 2. Again, the length is 2 pi. So sometimes we see that the expression is given, the mathematical expression, and we try to look into the graph of the given function and its periodic extension to get an idea how geometrically things are moving. Because when we look into the periodic function, so it means that graphically a certain portion of the graph is going to be repeated over and over again. And mathematically has got different expression, f of x plus p must be equal to f of x. Other than 2 pi, if a function is periodic with period, like 2L, for example, L is some arbitrary number is there. So yes, still we can find the series solution to that particular function. Formula is slightly different from the previous one where the function was periodic with period 2 pi over the interval from minus pi to pi. No, it is going to be defined over the interval from minus L to L with period 2L. So slight difference. And sine terms are there. So in terms of angle. And when we compute those coefficients, A naught, AN and BN, so we have slight differences over there. So here you go with examples. Yes, we see that all we need to know L. Once we have L, so you can go back to the formula, calculate A naught, AN and BN, plug in the expansion for the given function f of x. It's a piecewise function. And every time you see that when we look into those pieces, x is greater than minus 1, less than 0, 0 is not going to be a part. In the first part of the domain, x is less than 0. In the second part of the domain, different from the previous one. So this is how a piecewise function is going to be described. So different pieces of f of x are going to be defined against different parts of the interval. The interval is basically from minus 1 to 1. So minus 1 to 0 and then from 0 to 1. So we see that clearly 0 is not going to be a part. So this is how we see that it is going to be discontinuous. And one of the advantage over the Taylor series expansion, the Fourier series expansion has an advantage that discontinuous function could be handled by utilizing Fourier series method in comparison of Taylor series. So idea is there for the Fourier series method that we have to calculate coefficients A naught, AN and BN. Sometime, yes, we could eliminate unnecessary calculations. We can reduce the computational cost while talking about the Fourier series. Fourier series means behind the scene we need to calculate Fourier coefficients A naught, AN and BN. So when this could happen, so based upon the idea of even and odd function. So if the function is even or odd, we can reduce computational cost. We can avoid unnecessary calculations in obtaining the Fourier coefficients. So based upon this idea, we will see that things are more simple in comparison of the previous. Previously, we have seen that every time you need to calculate a naught, an, and bn every time, whatever the expression is there. But in a couple of examples, we have seen that sometimes you see a naught is 0, an is 0, but bn is non-zero. So if a naught is 0, an is 0, there is going to be an advantage behind the scene based upon whether the function is even or odd. So we will get to know, do we really need to calculate a naught? Because eventually it has to be 0. Do we really need to know or need to calculate an because eventually it has to be 0? Or sometime we see that bn is equal to 0. So no need to calculate this one. So we will develop a criterion behind the scene. So beforehand, we can say that since the function is of such type, so no need to calculate those coefficients. They eventually are going to be 0. So idea is based upon the concept of even and odd function. We all know about an even function, what an even function is there. Mathematically, we say that if you replace x by minus x and we get the original function back, so we say that a function is said to be even function, like in this expression f of minus x is equal to f of x for all sort of values of x. Take an example, x square, for example. If f of x is equal to x square, replace x by minus x, again you will get x square, means f of x. So f of minus x is equal to f of x when f of x is x square, x4 cosine nx, x square minus 2x square plus cosine x. So these are a few of the examples of even functions. Mathematical formulation is there. But geometry says that the graph of an even function should be symmetric about the vertical line. We will be having same portion of the graph on either side of the vertical line. So pretty simple example, like if you plot x square, it's a vertical parabola. So you will see that there is image in the first quadrant and the pre-image is in the second quadrant. You have the same portion of the graph on either side of the vertical line y-axis. So graphically, geometry states that graph of the function should be symmetric about the vertical line. Mathematically, f of minus x should be equal to f of x. So this is how we say that a function is said to be an even function. To the other end, odd function, if f of minus x is equal to minus times f of x, means by replacing x by minus x, we get the original function back, f of x, but with the negative sign. For example, x. So if f of x is equal to x, replace x by minus x on both sides. So you will see that the answer is going to be minus x. And what is x? It's f of x. So in other words, f of minus x is equal to minus times f of x. Same is the case for x cubed sine nx, x5 minus 3x cubed plus 2x. There are few of the examples of odd functions. So even function, geometrically, we see that it is going to be symmetric about the vertical line, whereas the odd function should be symmetric about the origin. When we observe the symmetry about the origin, it means that we need to look into the opposite quadrant. Like in the first quadrant, we all know x and y are positive. So you need to look into the quadrant opposite to that, where we have x and y, both are negative. So it is going to be third quadrant. So if you plot the graph of x, for example, f of x is equal to x. So it will pass through the origin corresponding to the first quadrant. You will be having the same portion of the graph in the third quadrant, symmetric about the origin. So If geometrically function is symmetric about the vertical line, function is going to be even. If it is symmetric about the origin, function is going to be odd function. Mathematically, if you replace x by minus x, you get the origin function back, function is even. If you get the origin function back, but with negative sign, function is going to be odd. A function, not necessarily an even or odd, as a very special case. Sometimes we could have a function neither even nor odd. However, a given function can be expressed as the sum of an even and odd function. Function is neither even or odd, like, for example, f of x is equal to e raised to power x. What happens if you replace x by minus x? It will turn out to be e raised to power minus x, different from f of x. You can never get back the original function. F of x equal to e raised to power x. You will get e raised to power minus x. You can't take minus common out of that. So we say that e raised to power x is an example of a function which is neither even nor odd function, but it can be expressed as the sum of an even and an odd function. Since f of x could be written as f of x plus f of minus x upon 2 plus f of x minus f of minus x upon 2. Now, if you look into the first part or the first term to the right hand side inside capital parentheses, we see that this is going to be even. This whole thing is going to be even. You can name it, for example, it's g of x. G of x is equal to f of x plus f of minus x upon 2. Replace x by minus x, you will get this combination back, this whole thing. So this part is going to be an even, and that one, if you take this one, for example, h of x is equal to this one, replace x by minus x, you will get this function back, but with the negative sign, minus outside this parenthesis. So you will see that this part is going to be an odd function. So f of x could be expressed as the sum of an even and odd function. For example, if you take e raised to power x, e raised to power x could be written as e raised to power x plus e raised to power minus x upon 2 plus e raised to power x minus e raised to power minus x upon 2. So this second term will cancel out if you break those parentheses, plus e raised to power minus x upon 2 and minus e raised to power minus x upon 2. They will cancel out. You will left with e raised to power x upon 2 plus e raised to power x upon 2 means exactly equal to e raised to power x. So this is how e raised to power x could be expressed. What is the first term to the right hand side? It's basically cosine hyperbolic x. The second term is sine hyperbolic x. And we know that cosine hyperbolic x is an example of an even function, whereas sine hyperbolic x is an example of an odd function. So e raised to power x been expressed as the combination of an even and an odd function. Now we look into the proof. Few results are there to be utilized later on. The product of two even or product of two odd functions is always even. The second part, the product of an even and an odd function is going to be odd. It is just like, think about it, plus sign and negative sign.
क्या लिया है मैंने नहीं दिखाई
Please mute your microphone. Yes, please, 186. One 186, do you want to say something? All right, so we move on. We need to show that the product of two even or the product of two odd functions is always even. The outcome is going to be an even function. But when you take one odd and one even, the product is going to be odd. Surely, it is just like the product of plus and plus is equal to plus, and the product of negative quantity with negative quantity is again plus. So let h of x is going to be a product of f and g, for example. Initially, we take start from here. Then we move on with the situation. In the first case, the product of two even functions. So we assume that both of them are even first of all. F is even and g is also even. So if f is even, it means that f of minus x is equal to f of x. G is even means g of minus x is equal to g of x. But here we need to ensure that the product is going to be even. So product is going to be h. H of x is equal to f of x, g of x. So what the criterion is it? H of minus x should be equal to h of x. So what we do? Replace x by minus x on both sides. So f of minus x, g of minus x. Since f is even, g is also even. So f of minus x would be f of x, g of minus x would be g of x. So what is f of x, g of x? It is h of x. So eventually h of minus x is equal to h of x. Means the product of f and g, where both f and g are even functions, is even. Or we need to take the second part of this statement, two odd functions. Now we assume that if f and g are both odd functions, means f of minus x is equal to minus times f of x, g of minus x is equal to minus times g of x. So replace x by minus x on both sides. So f of minus x is equal to minus times f of x. G of minus x minus times g of x, because g is also odd. Now minus into minus plus, so again it will turn out to be h of x. So h of minus x is equal to h of x, means h, which is the product of two odd function, in this case is again an even function. So product of two even or product of two odd function is even. So then you need to look into the second part. Take one of them as an even function and take the other one as an odd function, and then you can easily look into the proof of that. We take certain examples instead of symbolic representation like f, g, and h. We all know that xk is an example of an even function. Cosine of x is another example of an even function, whereas x cube is an odd function. Sine nx is another example of odd function. So if you combine them, xk, cosine nx, so it will turn out to be even function. Means the product of two even functions is again an even function. If you take the product of x cube with the sine of nx, product of two odd functions, again you will see that it is going to be an even function. On the other hand side, if you take one function from here, like xk, other from there, like sine nx, so this product of an even and odd function is going to be an odd function. Particular examples are there. Rather than talking about f, g, and h, we have taken certain example where we see that yes, product of two even, two odd is going to be even, but the product of an even and odd function is going to be an odd function. Let f of x be defined over the interval from -a to a. Then we have to show that if f of x is an even function, then the integral over the interval from -a to a is going to be 2 times over the interval from 0 to a. 0 to a is half of the interval, from -a to a. So if the function is even, so then this integral would be equal to 2 times the half of the integral from 0 to a. But on the other hand side, if f of x is odd, then this integral from -a to a is going to be 0. If f of x is odd, take a look. We take start with the integral over the interval from -a to a, and then split into 2 pieces, -a to 0, and then from 0 to a. So we take the first integral to the right hand side of this equation and put x is equal to -t, for example. So when you replace x by -t, means we have to replace dx. We also replace those limits, the lower and the upper limits as well. So everything is to be obtained from this expression x is equal to -t. So if x is -t, then dx would be -dt. When x is -a, t will be a because minus will cancel out. When x is 0, t will also be 0. So this is all. The upper limit is going to be 0 with respect to t, but the lower limit is going to be changed, a. X is replaced by -t, and dx will be replaced by -dt. Minus is taken outside the integral. And if you swap the limits, so you need to adjust the negative sign. So negative is going to be adjusted by swapping the limit. And then eventually we can say that yes, change variable property will take us to 0 to a f of -x dx. Change variable property. T could be replaced by x. So -a to 0 f of x dx is equal to 0 to a f of -x dx. So replace this one over here in that equation number 14. So we will be having integral over the interval from -a to a as sum of the integrals. Both are against the interval from 0 to a. It's f of -x and then f of x. No, it all based upon the requirement. So we have to see when f of x is an even function. If f of x is even, then f of -x would be equal to f of x. And in the second part, if f of x is odd, then surely f of -x is equal to minus times f of x. So until equation number 15, you have to look into this procedure, and then you take part number 1 and part number 2. So take part number 1. If f of x is an even function, then of course f of -x would be equal to f of x, and from this equation, replace f of -x by f of x. Identical things are there, so combine them, so it is going to be 2 times 0 to a f of x dx. But If f of x is an odd function, then surely f of minus x will be minus times f of x. So that one, f of minus x is going to be replaced by minus times f of x. So minus is taken outside. Identical things, but due to opposite sign, they are going to cancel each other effect and we left with 0. So this is all. We have the proof. Any function defined over the interval from minus a to a, if f of x is an even function, then this integral would be 2 times over the half of the interval. But if f of x is odd, then this integral is going to vanish. Now, based upon this idea, based upon the concept of even and odd functions, we move on to the series now. Everything is there. We have discussed extensively, talking about the concept of even and odd. Certain type of the integrals are also discussed. So now we move forward and talk about the Fourier series based upon the concept of even and odd function. If f of x is an even function which is also periodic with period 2L and defined over the interval from minus L to L, then show that a naught in this case would be 2 upon L, 0 to L. So remember, in the previous case, it was something like 1 upon L minus L to L. No, because an interval from minus L to L is basically 2 times 0 to L in case when f of x is an even function. We just have proved that one. Interval from minus a to a is 2 times 0 to L. So pretty much the same formula that we already have discussed in the previous lecture. All right, before we move on, let me generate a poll, because sometimes things are out of control. So I generate a poll for attendance purpose. (186), you did raise your hand, that is why I asked you. So raising hand means you have some query. So today is 12th of August 2020. And we are looking for present only. Here you go. Poll has been created. Mark your attendance appropriately over there. All right. So if the function is an even function, so what we say, there will be a naught to be calculated by utilizing this formula. An would be there, but Bn is going to be 0. No need to calculate Bn if the function is an even function, because eventually Bn has to be 0. If the function is an even function, Bn has to be 0, so no need to calculate that. If you do check before calculating those coefficients, whether the function is even or not, if the function is even, no need to calculate Bn, because eventually it is going to be 0. Then of course you need to calculate A0 and An by utilizing these formulas. And the corresponding Fourier series would be like that, without Bn, because eventually Bn has to be 0. So now you see that based upon the concept, whether the function is even or not. So if it is even, we can avoid unnecessary calculation behind the scene. No need to calculate Bn, because if you do, eventually it is going to be 0. So you can reduce the computational cost by checking whether the function is even or not. On the other hand side, if the function is odd, even simple, A0, An, they are going to be 0. If the function is an odd function, only you need to calculate Bn. Once you calculate Bn, plug in over here, and there you go with the corresponding finite geometric series. Series solution will be obtained if the function is an odd function. You must have gone through in the previous lectures. An example where you calculate A0, 0, you also calculate An is 0, but Bn is non-zero. It is because the function was an odd function. Now we have got an idea. If the function is odd, no need to calculate A0, An, just declare that with the argument, since the function is odd, so there must be A0, 0, there must be An 0, only we need to calculate Bn. And the simplest form of the Fourier series would be like that. So in these two theorems, we have taken the interval as 2L, defined over the interval from minus L to L. What happens if you take the period as 2 pi, defined over the interval from minus pi to pi? Then, if the function is even, the Fourier series would be like that, because Bn has to be 0 for even function. So A0 to be calculated by utilizing this formula, An to be calculated by using that formula. So slightly different, because of the angle is going to be different in particular. So we have to calculate A0 An in case if f of x is an even function. And on the other hand side, if f of x is an odd function, periodic with period 2 pi, defined over the interval from minus pi to pi. So the simplest one, only you need to look into the calculation of Bn's. Bn, they've been obtained, B1, B2, B3, by utilizing this formula. So once you have Bn, plug in all these values of Bn for certain values of n, expand this summation, and this is how you will be having the corresponding infinite geometric series. It's much easier, we have seen that. In comparison of the previous calculations, now, if you describe beforehand whether the function is even or odd, then we can avoid unnecessary calculations in order to calculate those Fourier coefficients. Sometimes the combination of A0 and An is 0. in case if the function is odd. Otherwise, Bn is to be 0 when the function is even. So in both cases, whether the function is even or odd, our computation cost would be significantly reduced. Take these examples. Find the Fourier series of the following functions. Sometimes this is that, yes, the geometry is given. Geometry is given, and you need to write it down the expression. And sometime we will be having expression, the mathematical formulation. And from the mathematical formulation, you need to go back and see the geometry. Take a look at the first part, plot the graph, and see graphically. Mathematically, we know the criterion. If f of minus x is equal to f of x, it means that f of x is even. And if f of minus x is minus time f of x, the function is odd. Sometimes it is a bit complicated, a bit demanding, not very complicated. It's a bit demanding when we have pieces of the function. Function is defined as piecewise. So better off to go back and look into the geometry. So plot this graph. Two pieces are there over the interval from minus pi to 0 and then from 0 to pi, minus x and x. So plot them and then see the geometry, whether it is symmetric about the line x-axis or symmetric about the origin. Second one is much easier. You can also look mathematically. F of minus x would be equal to minus time f of x. Or you can plot this graph. So you will see that it is going to pass through the origin and also symmetric, because same portion of the graph lies on either side of origin in the first and third quadrant opposite to each other. Try example part number 1 of this example. Try yourself. We got some time, and if you have any difficulty, we can discuss.